Okay. First of all, thanks for the organisers for allowing me to speak here and inviting me over. This is the second talk on proof complexity. So earlier Olaf talked about proof complexity, and here we mean the same thing. We're talking about proof size. However, as mentioned earlier, we can study proof complexity for things that are outside classical propositional logic. And here we're looking at proof complexity for quantified Boolean formulas. And this is joint work with Olaf and Mikuláš Janota from Lisbon. So what we have done recently in QBF proof complexity is we've developed a new lower bound technique. And this lower bound technique relates circuit complexity to proof complexity. And we've used this technique to find exponential lower bounds for a number of QBF resolution systems. So in particular, we're looking at these resolution systems. We aren't looking at these stronger systems like these Frege systems or sequent calculi. So from these exponential lower bounds, we prove separation. So that's when we have that, that either one proof system simulates another proof system, but the converse is not true, or we have two proof systems which mutually cannot simulate each other. And this reveals the full picture of the QBF simulation structure for these resolution systems that we're looking at. This is something that we're not going to go into too much detail. We found another separation result using a different technique for another class of formulas. So first, I'd briefly mention SAT and how it relates to QBF, particularly not just QBF as quantified Boolean formulas, but the QBF problem itself. So SAT is, if we have a Boolean formula, we determine whether it is satisfiable or not. So here's an example, very easy example. We just have, we have two clauses here, and we find that there is a satisfying assignment for this. Namely, if we take x equals 1 and y equals 0, then we satisfy this formula. In QBF, given a quantified Boolean formula, so that is a propositional formula with Boolean quantifiers, determine if it is true. So if you've seen QBF before, you know what this means. And the answer would be that you'd set y equals x, and this would give you yes. So what this quantified Boolean formula means, well, these quantifications are shorthands for, well, they can be seen as shorthands for these connectives. So for example, we take this formula, and what we mean by this existential quantifier here is we take the inner matrix here, and we substitute 0 and 1 for where y is, and then take a disjunction of that. Likewise, for the universal quantifier over x, we take substitutions for x as 0 and 1. So here we do 0, here we do 1, and then we take the conjunction here. Since we've quantified everything, so here we're in a closed Phoenix form, we get constant values when we expand here. So we can evaluate this to true or false, and here we've got it to be true. So QBF has a nice relation to complexity theory. First of all, deciding QBF is p-space complete, but also we have that if we restrict the quantifier alternations of the QBF, we get sort of complete problems for each level in the polynomial hierarchy. So a good example would be in NP. We could take a SAT problem and write it as a QBF. We just take the formula itself and we existentially quantify everything, and we've got a SAT problem there. Namely, the same for TALT here. And also as we go up, we can do the same. So QBF is very nice. So I've given you one definition of QBF. So it's these formulas with these quantifiers, and these quantifiers are shorthands for connectives with these substitutions. But there's another way, and this is probably a better way of defining QBF, and this is from a two-player game. So here we're only looking at closed predix formed CNF QBF. So in order to illustrate this two-player game, we use an example. So this two-player game is a game played on the quantifier prefix. So we start from the left of the prefix, and each of the variables correspond to a turn. And we have two players, the universal player, the existential player, and the universal player. We start from left to right, and whoever's quantifier is appearing on that turn, that's whose turn it is, and they get to decide whether that variable gets set to 0 or to 1. And the existential player is trying to win the game by making the matrix true, and the universal player is trying to win the game by making the matrix false. It turns out that a QBF is true if and only if there exists a winning strategy for the existential player. Likewise, QBF is false if and only if there exists a winning strategy for the universal player. So these winning strategies, from the game, you have to sort of see these strategies as, if they're functions, then they're functions only on the variables that come before it for each of the variables that you're playing. So for example, we have this QBF here, and there's 2 rounds in this. But no matter what the universal player plays in the first round, the existential player can respond and always win. So the existential player always plays the opposite of what the universal player plays for u on the variable e, and will always win, as you might see. So if u is set to 1, this clause becomes satisfied, but this one is not satisfied yet. So the existential player can satisfy this clause by playing 0, and likewise, if this was set to 0, this would be satisfied and can satisfy this one by setting it to 1. So again, we're looking at this relation to SAT solving. So as mentioned earlier today, despite being an NP-hard problem, SAT solvers are very successful. However, QBF solving is at a much earlier stage. So like SAT, we use proof complexity as the main theoretical framework to understand the performance and limitations of solving. So now I'm going to talk a bit about the QBF proof systems, these resolution proof systems, and their relation to solvers. So there's 2 sort of solvers that are happening in QBF. We have these CDCL solvers, similar to the ones we find in SAT solving, and we also have expansion solving as well, where we sort of use the semantic definition of QBF and sort of expand these variables, expand these QBF out, and then use SAT solvers to solve them eventually. But the idea is that these give us 2 different flavors of proof systems, both of which use resolution in their core. And we have the weaker systems at the bottom and the stronger systems at the top. So first of all, I'll talk about Q resolution. So Q resolution was this CDCL one near the bottom. So Q resolution is it's the resolution rule plus another rule called for all reduction. So the resolution rule is very similar to the one that you find in classical logic, and that is that we have 2 clauses. They have this common variable of opposite polarity in each, and we can merge these into one, dropping this variable here. However, we have this condition here that we have this existentially quantified. And in order for it to be complete, so we want a refutation, so we want to end up with the empty clause, we also need some sort of rule to get rid of the universal variables. And for this, we have universal reduction. And what you do here is you take a clause, it's a unary rule, and this clause has this universal variable k, and this universal variable k has the highest quantification level in C. So here, highest means more right. So the rightmost quantification level appearing in the clause C. And from that, we can simply drop it. Unfortunately, I could have explained why this is all sound on the blackboard, but unfortunately, I don't think I have time. There's another condition as well on Q resolution, and that is that we aren't allowed tautological resolvents.
Sorry, the universal quantification inside C binds the variable k outside of it? I don't understand.
There's no quantification inside the clause.
Oh.
There's a big prefix before, and you just look at the variables inside C and find the variable with the highest quantification level of your original prefix. Okay. And if that's a universal variable, then you can drop it. So we don't allow tautological resolvents in Q resolution. We had this big sort of diagram with extensions of Q resolutions where we do allow these tautological resolvents in special cases, and also we can allow like universal pivots in some cases as well. But here, this is the most basic. This is the basic calculus where we only allowed these rules, and this allows it to be complete. So here's an example. We start with this QBF in the CNF matrix. We can take these clauses as axioms. However, we can't for all reduce these U literals because these E literals are of higher level and so block the universal reduction. But we are allowed to do resolution here. So we can resolve on pivot E and end up with a clause containing just U. And now, since U is the highest, is at the highest level within this clause, we can simply drop it and get the empty clause and get our refutation. So on the other side, where we had these expansion solvers, we have these instantiation-based calculi. So before we had a rule for existential literals and universal literals, and these rules were sort of getting rid of them. Now what we do is we only have one sort of literal, and that is these annotated literals. So we have an existential literal L, which is annotated by some partial assignment to universal literals. And we can simply use resolution as the main way of sort of dealing with this. So we only need this one rule to get rid of literals and get us to the empty clause. So the advantage of this is it gets around this restriction on the complementary universal literals, these tautological clauses, by allowing mixed clauses. So here we're allowed to have clauses where we have different sort of contradictory assignments in the universal variables on different literals. So here's an example. This would be a valid clause with annotated literals. So that's sort of like the framework of how these instantiation-based calculi can sort of form. An example of one is a very simple one, this for all expansion plus resolution, this expansion calculus. And here we just have resolution and an axiom rule. So in this axiom rule, we're looking at the clauses in the matrix, but we instantiate these clauses to these clauses of just annotated literals. We look at all the existential literals in the clause and annotate them by some complete assignment to the universal variables. And there's a condition on this complete assignment is that it cannot satisfy the clause. So this clause has universal variables, and this assignment is not allowed to satisfy it. So tau is this complete assignment, but this bracket notation means for each literal, we only take the partial assignment on the universal variables that are to the left of it in the prefix. So it only takes the part of the assignment that is to the left of it in the prefix for this literal. And we have the resolution rule, but the resolution we have to have that these annotations match for these variables. So these are fresh variables that occur when expanding these we're expanding semantically on the universal literals. So here's an example proof. We have, well, maybe I'll skip through this. These calculi aren't the definitions of these calculi aren't so important themselves for the results, and this is what we're going to get into. So you can, if you didn't understand what these calculi were doing, or you can't remember them, it doesn't matter. We don't really need them for these results. We just need a few facts that that have been proved about them. So we'll go through the simulations quite quickly. So we know that the expansion calculus simulates a tree-like version of Q resolution. And we also improve the expansion calculus to simulate Q resolution. And some of the stronger systems can simulate each other. However, between these two calculi, it was already shown that the expansion calculus cannot simulate, yes? So this example, so here we have these axioms, and we want to take them into axioms in the calculus. So for this one, we take both complete assignments because we're allowed to. However, for these ones, we can only take complete assignments that do not satisfy these original axioms. And these annotations appear on the existential literals that appear to the right of these of the universal variables. And then we can do a resolution rule on E1, and we end up with this mixed clause where we have two copies of E2 but with different annotations. And now we can resolve with this one to get this, and then here again, and we get the empty clause. So yeah, we know that this expansion calculus does not simulate Q resolution. So our new technique shows that the opposite is true, that Q resolution cannot simulate the expansion calculus. And in fact, even the strongest part of the CDCL proof systems cannot simulate for expansion plus resolution. So if we want to look at this basic problem between these two calculi, we already have that result. We need something that's hard for these proof systems but easy for expansion proof systems. And the previous separations all relied on these formula, which we actually found were also hard for these two calculi as well. So those are no good. We need something new. So if we look again at feasible interpolation, briefly go through this. We have a implication problem, and we know it has an interpolant in the intersection of the variables. We can extract, if we have feasible interpolation, we could extract in polynomial time the interpolant. And the clique coloring principle has large monotone interpolants. So the proofs are large in systems that have this property, this feasible monotone interpolation. And this is important because it transfers these large circuits into large proof sites for these when we have this property. So we do a similar thing here for Q resolution. So remember back to this two-player game between the existential and universal players. And remember that every false QBF has a winning strategy for the universal player. So the idea is to think that hard strategies may require a large proof. So if we have a difficult strategy for the universal player, we may have large proofs in our system, Q resolution, for example. And so we can see that the contrapositive is that short proofs, we may be able to find easy strategies. So some sort of strategy extraction. We then just need to find some false formulas with these hard strategies for the universal player. So we're looking at strategy extraction now. So the theorem is that if we have a Q resolution refutation of some false QBF, we can extract in polynomial time from the proof a winning strategy for the universal player, which can be represented as a decision list. So a decision list, the important part of a decision list is that it is a bounded depth circuit. So short Q resolution proofs give short decision lists, short strategies in decision list format. And yes, it can be expressed as bounded depth circuits. So something about bounded depth circuits is that parity has only exponential size bounded depth circuits. So that's what we're going to use as our hard strategy. But we need to somehow force this universal strategy to always compute parity. So we use this formula that sort of encodes parity here called Q parity. So what we do is we existentially quantify all the variables that are going to go into parity. We then add this universal variable here, and we say that we basically encode here that Z is equivalent to not parity, I think? Yeah, not parity. And I mean, it doesn't matter which way around it is. We then find that in order the strategy for the universal player is to always play Z as parity, so that one of these clauses will always be refuted. So if these X variables are parity, then you set Z to true, and then this clause is satisfied, but this clause is refuted. Likewise, if it was there was no parity, you'd set Z to 0, and then this clause would be refuted. And so we somehow we try to encode parity into CNF and QBF, and we do so using these sort of auxiliary variables, which represent sort of the nodes in the circuit that's in some sort of circuit that gives us parity here. And yes, the winning strategy. There's only the point here is there is a unique winning strategy, and that is that Z is parity. And here we can deduce from this that Q parity requires exponential size Q resolution refutations. So if you got a bit lost in that, here's the summary of what happens. We know that we can extract decision lift strategies in polynomial time. So short proofs will always give us short strategies. Long proofs could give us short strategies or long strategies. However, we know that parity cannot be represented in AC0 in polynomial size. In fact, it's exponential size. So these are long strategies. And so Q parity must have long proofs. Now we need to say why this gives us a separation very quickly. We had these auxiliary variables. In the expansion calculus, we proved that the two sort of annotations of these literals are actually equal inductively, and we can easily get a short refutation for all expansion plus resolution. So in summary, we've created a number of new results. Some of these results come from some other lower bound we found, but this one in particular and this one are from this new technique. So there's still a few open questions on these proof systems. Some of these systems, the ones at the top here, are not. The relation is not well understood yet. And what's interesting is that the formulas for the strategy extractions are always prefixed like this. We're wondering, can we use this lower bound technique for other types of QBF? Thank you very much.
Questions? So, I just ask what these gray ones on the right, I mean, to what extent are these implemented and used?
Okay, so, well, I mean, you have the solvers themselves, and you have these two kinds of solvers. And you can extract, so I think typically the proofs you extract from the solvers are usually these ones, I think. Right. But this was the first calculus defined, and then it found out that this was actually a sound calculus as well. And then these are just sort of extensions here which allow these universal literals to be resolved upon.
Any other questions? Oh, well, thank you.